Right. Actually, this talk is going to be in two parts. First part will be as short as I can manage, because that is going to be a part where I try and do what I think it was George Bush called the vision thing. But that's likely to be slightly on the embarrassing side, and so the shorter it is, the better, really. And then I will go on to what the title of my talk is about, with a very, very small interlude, which I'll come to when I get there. So the vision thing is all about a question which has been touched on several times. Just what will maths be like in 100 years' time? So there are two questions I want to ask. What is a good proof? And then a sort of special case of will there exist mathematics in 100 years' time, or will there be a conference like this in 100 years' time? And what I believe is that if there is a conference, then the mathematics that will be under discussion will be pretty unrecognizable to us today. Of course, we'll all be dead, but it would be unrecognizable. So, let me just have a brief history of consideration of the automation of mathematics. There have been various points in the last century where mathematicians have got a little bit worried that maybe what they're doing could all be automated. But there have been things that go against that, where we've all breathed a huge sigh of relief and said, yes, there's something for us to do. So the first obvious example were the results of Gödel and Turing, and in particular the insolubility of the halting problem, showing that there's no algorithm for just deciding whether you can, well, for proving theorems. But then as Gödel realized, this was pointed out by Professor Rabin, as Gödel realized, actually that's not quite the real issue. The real issue when we're doing maths is a bit more like, does there exist a short algorithm for finding a short proof? We're not interested if, so what if there was an algorithm that took 1 billion years to find a proof that was 1 billion strings long? That wouldn't really bother us too much, because that's not really actually what we're doing. So a much more relevant question is, does there exist a polynomial time algorithm for finding a proof of length n, if it exists? And that is a problem in NP, and therefore it comes as another big reassurance that most people believe that p doesn't equal np, and therefore we can't just sort of program our computers to search efficiently for a proof of length n. I can't resist. I hope Avi Vigdisson will forgive me if I just repeat a comment that he made in Zurich at the International Congress, where he said if p equaled np, then we might as well all go off and solve partial differential equations. And a third, much weaker piece of reassurance is the empirical evidence. I think there is a bunch of people who try very hard to produce automatic theorem-proving programs, and as far as I know, they may have done things that interest them, but they haven't really got terribly far. They haven't maybe the computer scientists can correct me on this, but as far as I know, there's not really a seriously interesting theorem, maybe that we know already, that a computer has been programmed to discover the proof of. I want to argue that actually this is not as reassuring as it looks, because let's just consider the following thing. When we do maths, we do manage to find proofs. Now, unless you believe, like Roger Penrose, that something magic is going on in our brains, then you have to say that we're not just doing a search for an arbitrary proof of an arbitrary theorem. We must be doing something that's possible. I don't believe that we in our brains can solve p equals np without knowing it. So what's going on? So that's the next question. If p doesn't equal np, how is it that we succeed in finding proofs all the time? And the answer is pretty obvious, that we're looking at a much smaller subclass of statements, and we're finding a much smaller subclass of proofs. By the way, another thing I should say is I'm sure that what I'm saying is totally unoriginal and well known to a lot of computer scientists, and maybe they can actually tell us in a discussion more of what's actually going on in this. This is just my babyish speculations. Now, one thing that I think distinguishes the proofs we actually find from just arbitrary strings of formal symbols that end up with the right answer is somehow they explain what's going on. They give reasons for things being true. And people often complain, well, I could follow all the individual steps and then the answers seem to drop out as if by magic, but I've no idea how the proof was discovered, and somehow you feel you don't understand the proof unless you've got something more than just the proof. So then we think, what is it that distinguishes these good, nice proofs from just arbitrary formal proofs. And that's just, I won't go through all this, it's just a quick list of the kinds of things that one might find in a nice proof. So e.g. that you can sort of say, this is our main idea, and then if we can prove this, this ought to imply this, and indeed it does, because we've got this subsidiary lemma, etc., etc. The ones in green, those are supposed to indicate things that actually might be rather difficult to automate because they involve things like, in this case, pattern recognition, which is a notoriously difficult problem in artificial intelligence, and sort of basic, vaguely stated ideas. Of vagueness and computation at the moment don't really mix very well, but the point I would make is that although I'm not claiming that it's easy to automate the sort of maths we do, I don't think 100 years is a long time. What do I mean? Long or short? I think it will be done within 100 years. So I agree with Gromov on that particular point.
Which is what? What is it?
Gromov thinks that even in 2050, everything that we do will be automated. I don't maybe go quite as far as that, but nevertheless, I think a lot of progress will be made. The last thing I think is perhaps the most important of these 6 points. What we really like is not just a proof, but some indication of how the proof was discovered. We like to feel when we read a proof, oh yes, I could have thought of that if A, I had spent a lot of time on it, and B, I'd been 3 times as intelligent as I am, or something like that. We don't like these sort of magic steps in proofs. Now, if you restrict attention to proofs plus indication of how the proofs were discovered, then perhaps if you can formalize that somehow, I don't claim that's easy, but maybe it could be done, you get something where it's easier to search for them.
Do you know whether comments are welcome, or you want to continue in discussion?
Well, I feel if comments happen, they will just go wild. Maybe it's better for a discussion of. And I think this sort of a proof plus indication of how it was discovered is not a bad working definition for an explanation. But then I need to elucidate slightly this idea of what counts as an indication of how something was discovered. Again, I just give very preliminary thoughts. All I'm really trying to do is not sort of have brilliant ideas about automating mathematics, but just to explain why I believe that it will be done. So I think what I'm really trying to do in explaining a proof and how it was discovered is to show that it was sort of generated by typical kind of mathematical reflexes that we have. I examined this special case and I noticed that this happened, and I tried to think whether it was true in a general case, and I discovered no, it didn't. But if you modify the special case, then you get something else, and I looked for a different proof in that general. That kind of thing. That's what I mean by an explanation. So I've just given a couple of examples of what I mean by mathematical reflexes. If you can somehow explain your proof as being generated by something like this, then it's perhaps a bit more like an explanation as well as a proof. And if you've got things like this, maybe computers can search for that sort of thing more easily than searching for arbitrary things. A couple more mathematical reflexes just to give the idea. Right. Actually, this one here, I think is quite important. It's quite an important part of doing math. I'm absolutely serious, because if your mind is a blank and you just sit there, you've wasted, you can waste a fortnight or something. Whereas if you've got some kind of habituation type mechanism that says, I've been here for an hour and a half, I'd better do something else, it's probably actually more efficient in the long run for looking for. Perhaps I say something against that. I think Klaus Roth was asked, how did you manage to prove all these wonderful theorems? And he said, because he was prepared to sit in front of a blank sheet of paper for 48 hours at a stretch. So maybe that's Roth. So maybe that's another topic for discussion. Now, even if what I've just said, even if it's not all going to be automated by 2099, it's hard actually to imagine a computer coming up with Wiles's proof of Fermat's last theorem or something like that. Even if that's not true, nevertheless, I think there could easily be some sort of intermediate stage which would still have an absolutely enormous impact on how we do mathematics. So here's a sort of fantasy dialogue between mathematician and computer, which I really don't think I'm sure this kind of thing would easily be possible by 2050. So the mathematician is considering the problem, which is a theorem of Roth, that if you take a dense subset of 1 to n, then it contains an arithmetic progression of length 3. So the mathematician says, is this thing true? And the computer replies, it's trivially true because you can just take d equals 0. So the mathematician says, yes, of course, I didn't mean that. I want d not to be 0. That's my definition of an arithmetic progression. So the computer then starts taking it a bit more seriously, suggests induction. Mathematician says, that's not a very promising looking approach. Try something else, please. But then maybe they mathematical reflex. Why not try and look at the best counterexample you can find? And greedy approach, absolutely standard thing to do. So this computer will be programmed with a few sort of standard things to try, and it'd be easy to work out. I mean, these are sort of exercises, and the computer, I believe, will be able to do simple exercises. And checks a random argument. The mathematician, actually the computer really should have thought of this, but the mathematician says, it's stupid just to take a random set. You want to take, this is a very standard trick again, take random sets and maybe delete a few things from it because you've got a few arithmetic progressions, and if you just delete 1 point from each, you can actually improve the bound. And the mathematician says, because we all believe that random is best possible, I think random is best possible here. The computer says, no, it's not best possible because I've just looked through a large database that's got all mathematical papers on it, and I've discovered that actually it's not best possible at all. And that's actually, I decided not to mention that example during the discussion before lunch. It comes into this talk, not just now, but later on. And then the computer has a really sensible suggestion. Again, just a sort of standard reflex within combinatorics, also parts of number theory. If you want to prove that something exists, like an AP of length 3, just try and count them and show that the number is non-zero. Mathematician says, yeah, okay, but how do you do it? The computer notices that we're looking at a linear equation. Fourier analysis is, again, an absolutely standard thing to try. You can't quite do Fourier analysis, but the mathematician has this, maybe a computer would be quite clever to have the idea of actually turning 1 to n into a group somehow, etc., etc. The computer does some routine calculations. And the point, I'll leave it here, but by the next slide the proof would drop out. So a theorem that was considered one of Roth's very nice results, although not quite as famous, of course, as his Diophantine approximation results, but nevertheless a very nice result of Roth, should be an exercise for a beginning research student by 2050.
How about 4?
Don't know what to say about it. Okay, so that's my main point about that. I'm going to turn to some sensible maths. Just before I do that, I've got a really self-indulgent thing to ask you now, a sort of favor. So just for my own interest, I want to take a vote on 2 questions. I want to take about 1 minute for this, no discussion about it or anything. So the first is to consider a question that's of interest to philosophers of mathematics. That's the question, do numbers exist? So I've got 4 possibilities for the vote. It's yes, no, it's a stupid question, or the 4th one is it's not a stupid question, but I don't know. Okay, so you've just quickly to decide. So the question is, do numbers exist? So can I just have votes for yes, numbers exist?
We have to have
Okay, what about no, numbers don't exist? And it's a stupid question? And it's not a stupid question, but okay, well, it's not a stupid question, but I don't know the answer. Okay, that's very interesting, actually. I believe it's a stupid question, but.
But you left out the quantifier. You mean does at least one number exist?
All right, does the number 28 exist? Does the number 28? If anyone wants to change their answer. Well, does the number 10 to the 10 to the 28 exist? So the second question is slightly more serious, but only slightly. It's a question of how worried people are by using things like the axiom of choice. So this one is, which do you prefer, an easy proof that uses, say, the axiom of choice and the continuum hypothesis, or a difficult proof that doesn't use them? So, of the same result. So votes for easy proof that uses AC plus CH.
Easy proof.
And difficult proof that doesn't use it. Did anybody abstain? Okay. Okay, thank you very much. Right, now the proper talk starts. Dear oh dear, I wasted nearly a third of my time, but over a third of my slides you'll be interested to hear. So, right. So let's ask a Gromov type question. How many ways are there of defining graphs? Now, of course, in a sense, it's incredibly easy to define a graph. You just draw any old bunch of dots and join some lines, and you've got a graph. But supposing I asked you how many ways are there of defining a graph with 10 to the 10 vertices, sort of reasonably defining, then obviously it's not nearly going to be 2 to the 10 to the 10 choose 2, because most of them you can't really reasonably hope to define. So the sorts of graphs that come up in graph theory, they're not actually all that many. There's not supposed to be a complete list by any means, but you've got a few regular patterns. Kn is supposed to be the complete graph of order n, Cn a cycle of order n, Pn a path of length n. Here's a sort of what's called a star, a binary tree, and the discrete cube. Then you can do things like taking products, quotients, modifying things by removing a few edges, etc., etc. 3 is very important for some purposes, clever constructions, and 2 examples that have been mentioned are Paley graph and the Ramanujan graphs of Lubotsky, Phillips, and Sarnak. 4 is the one I really want to focus on. So let's say 5 first. So this is a picture of the Peterson graph. It's a graph with some very nice properties, but you'd expect a few graphs to have very nice properties amongst the small graphs. So from the point of view that I'm going to be adopting, this doesn't really count as terribly interesting, but it is interesting for some other points of view. But random graphs. Now this in a way, if I allow that, then you could say, well, I have defined 2 to the n choose 2 graphs, more or less, but I've maintained that I haven't really. I mean, and the reason is that if you just take 2 random graphs, say with edge probability a half, of course they're different with very high probability, but they're not interestingly different. We could ask the question, how would you distinguish between 2 random graphs? Actually, that's very easy. You just look at, say, something like the degree sequence. That's the sequence of numbers which give you the degrees of the various vertices in descending order. Almost certainly those degree sequences will be different. And actually, this is not totally relevant, but it's relevant to an earlier question that came up, I think it was last week or yesterday or something, of Don Zagier, which was about the graph homomorphism problem. This is just a small remark about that, which is that most of the time, the graph homomorphism problem can be solved. This is a very well-known fact to computer scientists, because what you do is you take the adjacency matrix of your graph and you write down the eigenvectors and eigenvalues, and it's easy to check whether they're the same, except when you've got repeated eigenvalues. And so typically a graph probably won't have, repeated eigenvalues, so typically you can distinguish between 2 graphs quite easily. So it's only a very small subset of graphs where the difficulty arises. However, although that means that you can almost certainly distinguish between 2 random graphs, if you try and take a different point of view, somehow give some meaning to the idea that one random graph with probability a half is actually the same as another one, you can do it quite precisely. One thing to say is that one of the insights of Erdős and others, I think I should mention Rainey as well, is that a lot of properties, in fact nearly all the properties that one is interested in about graphs, in the random case will be either true with probability pretty well 1 or true with probability pretty well 0, unless you really cook it up to be not like that. Anyway, there's a sort of threshold, so you could organize for the threshold to be exactly at the probability you're talking about. But usually, the property will either be definitely true with incredibly high probability or false with incredibly high probability. And that means that if you take 2 random graphs, then they will tend to share the same properties. It just follows from that. But we can ask it in a different way. And now I develop a point that arose in a discussion just before lunch. What do we actually mean by a random graph? I don't mean the result of tossing a coin n choose 2 times, because maybe it comes up heads every single time, and then you don't want to call that a random graph. So what do we mean by a graph that sort of is random for our purposes? Now this is a different emphasis from the sort of emphasis in computer science. They would say a random graph was one that a computer can't tell is not random. Now I don't mean that here. So this is a slightly different thing which has turned out to be very useful in graph theory. I need one definition. If I've got two sets, A and B, of vertices in the graph, I'll call the density the number of edges that you've got where x is in A and y is in B, divided by the maximum number that could be. That would be if every x in A and every y in B gave rise to an edge. So it's a very natural notion of density. It's the proportion of edges you've got, it's the number of edges you've got as a proportion of the number of edges you could possibly have. So if you take a random graph and flip a coin with probability of half, you would normally expect that if you take two large sets, large doesn't actually have to be all that large in this particular case, if you take two large sets, then about half the edges that you could possibly get will be there. And this turned out to be a very good definition for a pseudo-random graph, not in the computational sense. In fact, graph theorists are careful and they call them quasi-random graphs. And there are, as was mentioned earlier, there are lots of equivalent definitions, and here are just three of them, but there are many more. So one is exactly this thing, that the density is approximately the same for any pair of large sets of vertices. Here, for this purposes of this definition, large is usually taken to be some fraction of n, like 1% or something. But you can obviously get tighter bounds, but that's another question. Another property is that if you take a particular h, like, say, a triangle with a little edge sticking out of it, then you calculate how many of those you'd expect to get. You do indeed get roughly that number. That's for all fixed small h's, so to speak, you get that number. Actually, as was also pointed out, if you just look at 4 cycles and you get roughly the right number of 4 cycles, that's already enough to prove that the graph is pretty sort of random in the appropriate sense. And in the third sense, which is relevant to a lot of other things, is the second largest eigenvalue of the adjacency matrix is pretty small compared with what it could be. So the other way around, I would say that you can talk about the Laplacian as well, but let's leave it this way around.
What do you mean by the second largest? In English. Right under, you mean the one?
So write down all the eigenvalues in decreasing order. Take the second one you've got. It's going to be roughly regular. So you know that the first one will be approximately given by the vector, which is 1 at all the vertices. And that'll be about n over 2. And then if it's random, then you can't somehow get another eigenvector. Maybe it's better to contrast it with some other case where you haven't got that. Supposing you had...
You mean the second smallest one or the second largest?
But it's the adjacency matrix rather than the Laplacian, so...
It's good to talk about absolute value.
Yeah, okay. Yes, I'm sorry, I don't want it to be a complete bipartite graph or something, so...
It's the second one, they all are. You mean all but one?
Yes, so that's implied by this. Yeah, okay, sorry.
It's easier.
So basically, the spectrum looks something like this. That's a sort of picture of the spectrum of the graph. Get rid of that one, slightly confusing. This is a sort of mingling of discrete and continuous. It's a graph with many vertices, so actually if you looked at it closely, you'd see that actually it looked like this. And I put them not in decreasing order when I wiggled like that. But
I want to be confirmed. It's very strange to consider that. The second smallest one I can understand.
we're obviously having a total communication thing because I don't find it at all strange to consider. But maybe that's another point for the discussion. Now, if we adopt the point of view that, where are we? We're not very interested in the difference between two random graphs, then we get something which could be regarded as a classification of all graphs. This is where, now that seems at first when somebody said classify graphs, it's an absolutely ridiculous thing because you don't really need to do that. You just take your set of all possible edges and just bung in some subset, and so it's like classifying sets or something like that. But it's not like classifying sets because a set of edges has a lot of structure according to the position of the vertices and things like that. Now here's a sort of schematic picture of a typical graph. What this is supposed to represent is something like this. Let's use this again. I've partitioned the vertices into 5 pieces, 1, 2, 3, 4, 5. Here I've filled it with a random graph with edge probability 2 over E, here 1/3. Along this, all the sort of edges between this set and this set, I filled up with probability 1/3, etc., etc. So it's not quite a random graph, but I've had to make 15 decisions about some probabilities and put those in, and otherwise it's random. Now, there's an amazing lemma of Semeradi, which, although it's amazing, is actually not too hard to prove, known as its regularity lemma, which has a huge number of applications, that says essentially all graphs look like this. So you can get any old graph by just partitioning it into some bounded number of pieces and putting the edges into those pieces roughly randomly, although possibly with different probabilities, and joining the edges between them more or less randomly. Actually, it's slightly misleading to talk about the edges within for reasons that will become clear if you look at the precise statement. It says for every epsilon greater than 0, you can find a partition into k pieces. I haven't said this, but k depends only on epsilon. And there's actually the more precise statement of the theorem is that you can make k bigger than some fixed m, and it has to depend on that m, and that's sometimes useful. But this is, for now, this is an okay way of putting it. You can partition the vertices into almost equal sets, so as equal as they can be, they're equal to within 1, such that almost all the pairs, all but epsilon of the edges joining blobs, span random graphs. And when I say span random graphs, I mean they span graphs that have these sorts of properties. So they behave, to all intents and purposes, like random graphs.
It's for every G.
For every single graph, you can partition it like this. Now notice you do have to throw away a few of the edges. It's proved by a sort of iteration. You start by finding a partition that slightly improves some quantity, and then if it's not already a partition like this, you can increase that quantity, etc., etc.
You should say that the K depends, how K depends.
I'm about to say that, yes. There is a drawback with this thing, which is that the best known bound for K is 2 to the 2 to the 2 to the 2 dot 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 to the 2, where the number of 2's there is proportional to 1 over epsilon to the 5th. So, nevertheless, this result does have many applications. It comes out of the proof, but actually slightly more than it comes out of the proof, because I have an example of a graph where the number of things you need in a partition is 2 to the 2 to the 2 dot 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 to the 2 of height epsilon to the 1 over minus 1 over 16. So 1 over epsilon to the 1 over 16. So it is actually necessary to have a large number of sets in the partition. That is a serious drawback. That's one of the main themes of my talk, actually. That's a big disadvantage of the theorem. But the fact that it exists at all is very nice. It's wonderful that we've got it because it has many uses. I'm just going to give you one. Oh, no, I've got something else to say before. Then I will just give you one possible way of using Semeradi's lemma. But this is just let's just cover that up from there. This is just to make slightly more formal what I mean by a classification of graphs. When you normally classify something, you define some equivalence relation, and you want to find a representative from each equivalence class. What I mean by a crude classification is, instead of putting an equivalence relation, you put a metric, and instead of finding a representative from each equivalence class, you want to find a delta net in that metric, or something like that. So here, and when I say a delta net in that metric, I mean a delta net of graphs that you can somehow describe in a nice way. And by a nice way, I mean you can actually use it. You can say, I want to prove this theorem. Well, actually, I've got a graph, and I know it must look like one of these graphs, and I can sort of just verify it for those graphs, dot, dot, dot. So it's sort of philosophically similar to how you use classification. So you could define the distance between two graphs by saying, let us look at how the number of edges between A and B differs from G to H as a fraction of 1 over n squared, where n is the number of vertices. And if that's always small, in other words, if all the possible densities in G are pretty similar to all the possible densities in H, then the graphs are, from this point of view, or from many points of view, more or less the same graph. So the statement that two random graphs with probability of half are more or less the same is a special case of this more general statement. Now, I haven't said what I mean by global properties. You could almost take this as a definition of global properties. But here are some examples. If I've got two graphs that are close in this metric, they will contain approximately the same number of small subgraphs of some given kind. They'll have a similar sort of spectrum and things like that. Now, what is one way of using that? Well, it's to justify the following statement. It's a very reasonable thing to think that if you take a graph G and you pick, say, half the vertices at random, then somehow the subgraph that you choose should be pretty like the original graph. But if you try to justify that statement without using, or to make sense of it and justify it without using Semiramis' lemma, it turned out to be quite difficult. And here's an example of something that I don't myself know how to do without using Semiramis' lemma, or in fact there's a weakening of Semiramis' lemma which gives a better bound, which suffices for this. But actually Semiramis' lemma itself, the full strength of it is needed for, as far as people know, for several other applications. So here's a slightly complicated statement. What it says is, suppose G had the property, maybe I can draw a picture, try and make this fit. Suppose G had the property that whenever you choose a set, so here's G, whenever you choose a set of half the vertices, which I'll call H, so that's for every H, you can find inside that a set K where the density is at least a third. So however you choose H, inside there you can find something with quite a lot of edges. It turns out that it must actually be, so that says every H has the property that it got, what was this, H was size n over 2k was size n over 6. So in any H you can pick a third of the vertices and get density a third. That must be true, since it's true for every H, it must be true for a random H. And then this philosophical principle, which I will justify in this case, says it must also be true of G. If you choose, so G must have a subgraph of a third of its vertices with density at least a third minus some small error. How do you prove that in this case? You just say, what is a random subgraph of this graph going to look like? With very, very high probability, you'll pick almost exactly half these vertices, almost exactly half these vertices, almost exactly half these vertices, etc., etc. By the fact that these graphs joining them are pretty well random, you find that all the numbers that you get in this subgraph are the same as the numbers that you had in the original graph up to an error of epsilon. And so in the subgraph you find your K. Your K will have a certain proportion of all these vertices, so you just double the proportion however you like, and that gives you the original. That gives you a similar sort of thing in the original graph. Now, if you try and prove that directly, it seems to be incredibly hard. So somehow, classification for a problem like that seems to be necessary. Although, as I say, I commented that Semiramis' lemma is not absolutely necessary. You can do it by a similar sort of what I would call classification argument. Now, the other part of my title was rough structure, so let me just give a theorem that exhibits that without trying to define what I mean by rough structure. And that's Feynman's theorem. It just says rough structure at the top. So first of all, I need to define a d-dimensional arithmetic progression. That is a set of the form. Now, if you set d equals 1, what do we have here? We have x naught plus, we have the set x naught plus x1, x naught plus 2x1. Perhaps it would be better if I put di there. But so much, I think it would have been better. Let me just quickly change xi to di for common difference. Anyway, that was a bad idea, wasn't it? Because I had d for the dimension. All right, so, and I've also got x naught. So this is a natural generalization of an arithmetic progression to something, and it's perhaps best illustrated with an example. This is supposed to be a two-dimensional arithmetic progression because I take an arithmetic progression of length 4 and then I take a progression of those progressions. And that gives me a two-dimensional arithmetic progression of length 4 in that direction and length 3 in that direction. So you can invent the definition for yourself if you didn't follow the thing up there. Now, if I take a set A of integers, I can look at its sum set, and that's the set of all possible sums of two things from that set. And there is a very interesting theorem indeed about what happens when the sum set is small. Now, just before we think about that, it's easy to see that if A is an arithmetic progression then of size n, then the sum set has size 2n minus 1, and actually the converse is easy. If the sum set has size 2n minus 1, it's an exercise to show that the set is an arithmetic progression. So Freiman considered what happens if you relax the 2n minus 1. And what happens is this. As the size increases up to 3n minus 4, A doesn't have to be an arithmetic progression, but it can be a subset of an arithmetic progression a little bit longer than A. And so it's clear that that will have a small sum set. If I take A to be a subset of 4/5 of some arithmetic progression of length 5 over 4n, you'll get a pretty small sum set. Suddenly, when you get from 3n minus 4 to 3n minus 3, I think I got those numbers right, a sort of transition occurs, and suddenly you're allowed to have two-dimensional arithmetic progressions, and as you get bigger you can have subsets of two-dimensional arithmetic progressions. And then the picture gets a bit hazier. It looks as though, if I assume that A plus A is at most Cn, then as C increases, gradually you're allowed three-dimensional arithmetic progressions, subsets of those, and so on. And that is indeed true, and that is the main theorem of Freiman, which says if A satisfies this property that's just a sort of numerical property, it counts the number of possible sums, then you can deduce from that an incredibly strong structural property. Now, by structural, the reason I call it rough structure is it's not sort of some algebraic thing, but it's a subset of a d-dimensional arithmetic progression where D is bounded in terms of C, and the size of the progression is, as a fraction of A, is also bounded in terms of C. And it's trivial that the converse is true. If you take a d-dimensional arithmetic progression, take a large subset of it, that will have a small sum set. That's another exercise that one can go away and check. So this, in a sense, gives a complete description of sets A with small subset. Now, the reason I say only in a sense is that the bounds that are known are very weak. And one finds that if one wants to improve the bounds, all sorts of interesting questions arise. And I should say that this theorem was reproved by Imre Ruger a few years ago with a proof that is in many ways more conceptual than the original proof of Freiman, and gives a better bound. But even the bound that it gives seems to be far from best possible. And I'll go stronger than that. As some people here know, I used Freiman's theorem in a proof of Samaradis' theorem, and I would be very interested, for the purposes of that, to have an improvement to Freiman's theorem. So I'm now going to mention some problems, and I should make a comment about all of them. They may look like the kind of, sort of fun and games that combinatorists like to do. What I want to convince you of is that there are good reasons for thinking about them, but I'm not going to have time to say about all the sort of places where some of these things can be applied. So I mentioned that Freiman, I'm interested in it not just because I like the problem on its own, but because I have things in mind that could be done with it. That's not true with everything I'm going to say, but it certainly is for some of it. So here are some problems that I think would be very nice to see done in the next, before the computers take over. So, first one has been mentioned already, and that's the bounds for Ramsey's theorem. We know that by Ramsey's theorem, every graph on n vertices has a clique or an independent set of size between log to the base 2n divided by 2 and log to the base 2n times 2. And putting it this way round, RKK is the least n that works in this theorem, and the known bounds are between 2 to the k over 2 and 2 to the 2k. 2 to the k over 2, as Noga said earlier, you prove in one line by taking the random graph and seeing what happens. And 2 to the 2k, maybe you take 2 lines if you do it by what I regard as the simplest method, which doesn't give quite the best bound, which is you say take a vertex It's either joined, let's have red-blue colorings. Take a vertex, either n over 2 of its neighbors are red or n over 2 of its neighbors are blue. Look at the subset where that happens. Take a vertex, either n over 4 of its neighbors are red or blue. Continue that process. That gives you a set of size log to the base 2n, and then choose half of those where you always chose red or always chose blue. When you see an argument like that, it's very, very tempting to try to improve it, because you say, what would happen in the worst case? In the worst case, you'd never be able to do better than choosing half at each stage. But that's absolutely wonderful. If you can guarantee that you'll never do better than choosing half at each stage, then why don't you just always choose red at each stage, and then you won't have to do the second stage where you pass to a subset of half of that log to base 2n. Well, I'm sure any combinatorialist in the room has tried to think along those lines. Actually, I think there's probably some meta-theorem, I haven't bothered to think about this, which says that any sort of simple-minded strategy where you say, well, if I've already chosen this number of reds and this number of blues, and the proportion is this, then I will go for this one. I think pretty well any strategy like that will not work. Sort of the devil can come up with some graph where that strategy will not do better than, in fact, it will actually do worse. But that's not a theorem, that's just perhaps I might even dare to call that a conjecture. I think I can formalize it. So the problem is basically, where is RKK? It's not even known whether RKK to the...
Since you didn't vote yet, can you vote which side you think it's going?
I have a soft spot for 2 to the k. But certainly I believe the upper bound can be improved. I don't know, but between 2 to the k and... The reason I believe 2 to the k is just because morally, most 2 to the k, morally it should not be necessary to do that second stage, although I can't translate that into a proof. That is sort of give or take sort of factors. Well, actually, this is actually a binomial coefficient.
That's not the problem. This is what's known, and the problem is to...
Yeah, sorry, no, the problem is to find the right answer. This is a huge gap. What's actually...
Perhaps take the k root, what's the limit?
But as I said, not even known whether there is a limit. So no sort of submultiplicativity or anything like that. Now I'm going to have to hurry a bit. The second one is where you are allowed to use R colors, and you want to make sure that there's no monochromatic triangle. What is the right bound for that? The best known bounds are basically e to the r and basically r to the r. What is the... the main question of interest is it actually a constant to the r? That's equivalent to saying how many triangle-free graphs do you need to cover all the edges of the complete graph with n vertices, and if you could prove that you always needed constant log n, that would give you e to the r. If you could do it substantially better than constant log n, like constant log n over log n, then it'd be more like r to the r. Again, I think that's a very interesting question. I'll come to in the next slide to why I like that question. The third one is a beautiful conjecture of, I think, of Erdős, maybe Erdős and somebody else. What happens if you say that your graph is not allowed to contain, say, a copy of this graph? When I say a copy of that graph, I mean you can find some vertices such as those ones are all joined and these ones are not joined. If you forbid that in your graph, what happens to the Ramsey bound? Now I'm getting really to a serious topic that I want to discuss. This forbids random graphs, because if I do the random graph, it will contain the expected number of these. So you're not allowed random graphs, but also highly structured graphs will, either they or their complements you can sort of trivially see contain these things. And so you're in a situation where random doesn't work and a lot of structure doesn't work for producing counterexamples. And Erdős conjectures that the correct answer is actually a power of k. So the upper bound comes down from exponential to a power. Something is known, but it's much, much weaker than that. So this thing about random not working and explicit not really working either, that is a sort of situation where I feel that something like classifications come in. You somehow then are forced to look at all graphs and say, I can't prove that you're forced to do it. Maybe someone comes up with a very clever argument. It's just my feeling that one is likely to be forced to do it. So why are these problems difficult, and it's related to why they're interesting? If you know why they're difficult, then they're interesting because if you did them, you'll have to overcome some difficulties, and that's probably going to be very useful to not just to you, but to other people and so on. So it's not very obvious what the extremal graphs are. So in Ramsey, people have been saying random is best for Ramsey's theorem, but as Noga pointed out, if you look at the very closely related question, you want to minimize the number of cliques of size k plus the number of independent sets of size k. You don't do best by taking random. Now, I thought that was due to Andrew Thomason, but he's, I think...
Actually, I mean, it's Thomason and then Franek and President. But you're right. Thomason is...
Now notice that this is not quite what was being discussed this morning. I'm not at all suggesting that you do better by choosing a Paley graph or something like that, because a Paley graph is pseudo-random in the sense that I described before, so it has the right number of, say, k4s. So it really turns out that the best graph is very different from random. I don't know what the details are, but it's something like one of these things. You choose about 4 blobs, choose clever probabilities between them, and compute the number of k4s, and it's less than you'd get in the random case. It's a very strange... You can prove for triangles that it is best, but for k4s, it's not. Now, once you see that, that again suggests that you're not going to be able to prove Ramsey's theorem by just saying some clever argument to show that random is best, because how are you going to... How's your argument not also going to say that it's best for this problem? The second point, bipartite graphs don't give the best triangle-free decomposition of the complete graph on n vertices. Here's a very simple way of doing better. And I'll give a slightly less simple just in case you are encouraged by this. So the simple way of doing it is to take 5 blobs. So if you're interested in sort of this global graph theory, you begin to get to like blobs. And so you have 2 graphs. Here's one triangle-free graph. I'll join all edges between adjacent blobs. And then here's another one. I'll join all those edges. So with 2 graphs, I've managed to get all edges except the ones inside the blobs. Now I can just iterate that inside the blobs. So how long does it take me to do the whole thing? It takes me log 5n steps times 2. And so that's log root 5n. And how long did it take if I do it with bipartite graphs? I take 2 blobs, and then inside there I take 2 blobs, and inside there and so on. That takes log 2n. And this is smaller. And you can do better than that. For example, if you take 41 vertices, for 41 blobs, and you number them from 0 to 40, and you take the subgroup of Z40, consisting of all 4th powers, and you join 2 blobs according to whether the difference in their labels, which coset of this subgroup they belong to, then actually this was an original motivation for this problem of Schur. A triangle corresponds, it's easy to check, to a solution of x to the 4 plus y to the 4 equals z to the 4. So he was using it to show that Fermat's last theorem can't be solved for some trivial mod p reason. And you can just check that no 2 4th powers differ by 1. So if you divide by z to the 4, you can go for that. It's easy to check that no... Oh, well, actually, I had an a times everything. You can check that the 10 4th powers, no 2 of them differ by 1, and therefore you've got a triangle-free decomposition of 41 blobs into 4 graphs, and you get 4 log to the base 41 n, and that improves on 2 log to the base 5n. Perhaps I've convinced you now that the extremal graph is not obvious. Certainly don't think it's that. Actually, this also goes back the other way. If you've got a really good bound for this, it would have non-trivial number theoretic consequences, although I'm not sure whether maybe they're known by other reasons, I'm not sure. And yeah, so for 3, I just feel I have no idea what's going on. I've already mentioned this, that you try random, sort of highly structured examples, you can't get anywhere. You try completely random things, you can't get anywhere. So somehow you're forced to look at what goes on in between, and that I regard as the sort of area where classification in this rough sense comes in. For the third problem, it's terribly tempting to try to use some sort of form of Semirades lemma. So basically your graph looks like this. If you ever... So let's again say we've got a graph, we've got some blobs. Let's call an edge black if you've got almost all the edges, white if you've got almost none of the edges, and grey if you've got something in between. Now supposing you could find 1, 2, 3, 4, 5 blobs where all the edges were grey, and because everything looks random, it turns out that you get lots of copies of this graph. So that sort of implies that you don't get very many grey edges in your blob graph, but somehow that doesn't help, partly because the bounds from Semiramis' lemma are too weak, and partly because even if you fantasize about sort of false versions of Semiramis' lemma that you might be able to use instead, it somehow still seems to be difficult to use. So now I've got to rush on. So perhaps I just won't be able to say so much about these problems, unfortunately. So this problem here, problem 4, is what is the best bound for Rowe's theorem on arithmetic progressions of length 3? I'll just say there is an enormous gap. This upper bound here is due to Bourgain, and the lower bound is a thing of Berend that I mentioned earlier. And Feynman's theorem, I've already mentioned that. Good, so I can go a bit faster. These ones are hard because Fourier analysis, although it's very, very useful, is not quite perfectly designed for the problems. It's a similar problem to the one that Peter Jones mentioned in his talk. Things like if you take a characteristic function of an arithmetic progression and look at its Fourier coefficients, there are quite a few large ones, not too many large ones because there's a quick decay, but nevertheless there's more than just one large one. And in the proofs you tend just to use the number of large ones and their sizes, but the large ones you get for a characteristic function of an AP have a very strong arithmetical properties. You know, they lie sort of roughly in an AP itself. And it's not easy to find a way of using that in the case of more general sets. And so again, you somehow feel sort of forced to classify things. Classifying subsets of Zn, it's a similar sort of thing to classifying graphs. And I put a dictionary there. If you take a subset of Zn and you define a graph on Zn by joining x and y, if y minus x belongs to that subset, so it's actually a directed graph, then you can translate many things. Eigenvalues of the adjacency matrix become Fourier coefficients, and pseudo-random becomes pseudo-random, and so on. So they're philosophically very similar. I do want to mention one more problem just to show this classification thing goes beyond combinatorics. Supposing you've got a subset of the unit sphere of R to the n in the L2 norm, which intersects every n over two-dimensional subspace. What happens when you blow it up? Does it contain the unit sphere of some k-dimensional subspace? Now this is carefully chosen so that concentration of measure won't work, because one possible candidate for A would be the unit sphere of an n over two-dimensional subspace itself, which intersects every other one by reasons of linear algebra, but the measure of A epsilon is not almost 1, so you can't use concentration of measure. However, it trivially, when you blow it up, does contain a k-dimensional subspace. So you've got this example, this sort of very structured example that doesn't work for sort of one reason. If you try and hit every subspace by a random method, then when you blow it up, you sort of fill up the whole sphere, because if you chose a random thing, then blowing it up is a disaster. So in order to understand this problem, you've somehow got to understand what goes on in between. Again, you somehow want to classify or describe in some useful way subsets of S. And I won't bother with question 7. Question 8 was one other thing, just a beautiful problem of Danza. Can you find a subset of R squared which intersects every convex set of area 1 in at least one point? It's enough actually just to consider rectangles, but you're allowed to rotate them, but doesn't accumulate anywhere. So you can't find, I put 10 to the 100 just to give some non-canonical number, but you can't find a convex set of area 1 containing lots and lots of the points. If you could, you'd have a very, very beautiful, I don't believe you can, but if you could, you'd have an absolutely beautiful set, because it would approximate the uniform measure even when you applied affine transformations to it. I'll just say one thing, one example that might occur to you after a moment's thought is to take a lattice and a rotation of the lattice by some cleverly chosen angle. And there's a paper that proves, not by me, a paper that proves that that example doesn't work. You can't use a finite collection of lattices. Right, I will end by just, I won't say anything, I'll just put one slide up because I must stop. But you can just read that if you feel like it. But it's sort of covered. I think it probably doesn't exist, and the proof that it doesn't exist would be very, very interesting. But I only mention it just because random, if you choose a random set, that fails, because with probability 1, it will accumulate somewhere. And if you choose an explicit set like a lattice, it's very easy to find big convex sets that miss it.
That would imply some area.
No, it's got, this has got nothing to do with...
Well, see, if we have increased density in
maybe. Okay, so I've followed the usual trend, and so I better stop.
Thank you.